In this class, we're going to have a look at more fundamentals of probability. This includes things like conditional probability, independent, and mutually exclusive events. Enjoy! Okay, so for this class, we're going to continue the theme of the previous class 1, which was to cover some more fundamentals of probability, starting with conditional probability. So, at its core, conditional probability is effectively just going to reduce the sample size of what we're looking at. So if we look at this particular example using a Venn diagram, we have this scenario where a six-sided die is being rolled and we want to find the probability of rolling a number greater than 3 with the special condition that we've rolled an even number. So that kind of terminology is very common for conditional probability, the keyword given. Pretty much whatever follows the word given is your conditional. It's the restriction that you put on your probability, and the stuff after the word probability is the target probability that you're aiming for. If we were to draw a Venn diagram contrasting those two events, rolling a number greater than 3 and rolling an even number, it would look like this. You'd have these numbers in the center and then numbers that just don't belong to either of those sets. Normally, if you're just trying to find a number that is greater than 3, or the probability of rolling a number greater than 3, that's just going to be 3 out of 6. There's 3 numbers that are greater than 3 out of a total of 6 possible options. When we're specifically looking for the conditional probability here, we're now given that the number that was rolled was even. So we ignore the overall sample size of numbers 1 through 6 and we just look at the even numbers. This becomes our new sample size. We ignore the 5, we ignore the 1 and the 3. These are the only possibilities now that we look for within the new sample space. When you look at that, there's only 2 numbers out of a total 3 that are greater than 3. So there's now 3 total left, 2 of which are numbers that are greater than 3. Hence, your conditional probability is now 2 out of 3 for that particular scenario. This is the syntax that you use for conditional probabilities. You use this pipe, this vertical line that separates the probability that you're looking for, in this case, rolling a number greater than 3, separating that from the conditional, in this case, rolling an even number. More generally, if you abstract that to just 2 events A and B that are contrasted together, the conditional probability A, given that B has occurred, is always going to be the intersection of those 2 events divided by the conditional, whatever that is. So if we again look at the Venn diagram that we have, that was what this bit was, right? Probability of even is going to be all of this stuff in here, and then the conditional was the intersection within that. So intersection divided by conditional. If there's anything I should clarify further there, let me know. Otherwise, I'll continue. There's another example here on using the actual conditional probability formula itself. So you don't always have to create a Venn diagram, although in a fair few circumstances it's probably still a bit more effective. This is just another method by which you could solve it. So in this case, we have a group of 24 students and we're told the relative proportions of who studies what, math, physics, or both. The probability, or at least the question being asked of us is, given that a student studies physics, what is the probability that they also study math? So again, keyword given, whatever comes after the keyword given is the conditional. So in this case, conditional is going to be physics. Whatever comes after the word probability, that's going to be the target probability within that restriction. I'll pause a second and just contrast this order of the phrasing to the previous question we had. This one said given first, probability next. This one up here said probability first, given next. So those terms might be written back to front, but it still maintains the case that whatever said immediately after probability is the thing you're looking for. Whatever said immediately after given is the restriction. So even if these are in different orders, you still follow that notation. That gives us our conditional probability notation. From there, we just plug in the plug in the blanks where they would have been. So we need the intersection of those two events, and we want to divide by the conditional of that thing. So our goal is now to just find the intersection and the probability of the conditional. Well, the intersection probability, we're told 8 study both physics and math out of a total of 24 students. So 8 out of 24. When you're solving these, because these aren't the final thing that you're looking for, it's okay to leave these unsimplified. In fact, it's better to leave them unsimplified because, as you'll soon see, if you do so, it's pretty likely your denominators will cancel out. But anyway, that gives us the intersection we were looking for. Now we just need the probability of our conditional. There's 12 who study physics out of a total 24, hence the probability of physics, 12 out of 24. Now we just divide the two. Intersection divided by conditional. There's our intersection, there's our conditional. Performing that division means flipping that division sign into a multiplication and then flipping the fraction. And as you can see, as I pointed out before, denominators are pretty likely to cancel out, leaving this simplification usually significantly easier. Anything to clarify there? Let me know. Otherwise, we move on to example 3. Okay, so another way you could solve conditional probabilities is with tree diagrams. Tree diagrams, by their very nature, imply conditional probability, because if we just take a sneak peek at the tree diagram that we have, the only way you ever get to this spot on the tree diagram is if you have gone through branch A. There's no other way to get here. That means that getting here is conditional based on this. So this right here, all of these are conditional probabilities based on what happened previously. In this case, we have company is producing motors on assembly lines, and we're told specific fault rates for each assembly line. In 1 hour, 40 motors are produced on line A, 50 are produced on line B, and at the end of the hour, they basically get all chucked into a box, and then one is selected. We want to figure out the probability that that motor that is selected is faulty. So first thing we do is set up our tree diagram. So first things first, you'd want to select between line A or line B. Those are going to have a 4 out of 9 and a 5 out of 9 chance respectively. Does anyone either remember or could figure out why these are 4 out of 9, 5 out of 9?
Because there's total 90 motors,
Mhm.
and then for line A, 40 motors are produced,
Mhm.
and so that's 40 over 90, which simplifies 4 over 9.
Yep.
And then line B is 50 over 90, which simplifies to 5 over 9.
Perfect. That's those. And then each of these probabilities, those are a bit more straightforward. 5% on line A are faulty, which is why 0.05 for faulty on the line A one. That leaves a total probability of 0.95 left over for it being not faulty, and then a very similar scenario with the 8% faulty on line B there. This gives you your tree diagram, and then you just, at that point you can answer any question you want. In this case, probability of faulty, well, you can either get here for faulty or get here for faulty. So you would do this times this and add it to this times this, which sure enough is what's going on here. Simplify, simplify, simplify. Up to you whether you want to work in terms of decimals or in terms of fractions. I find most people tend to like working with fractions significantly easier, so that's why I've written this one instead. But if you can do decimals well enough, then by all means. Anything to clarify there? Let me know. This one here is also pretty common. So you'll get a table of data here. You could just go back to fundamentals where you just use the conditional probability formula and then just use the information provided to you there to solve it. Although I will show you a shortcut, which is kind of like how the Venn diagram restricts for that conditional, so too does it for table of data as well. So in this case, we have use of medication contrasted with age. So they're either yes or no, as far as whether they use regular medication and whether they're greater than or equal to 30 in age or not. And so in this case, the conditional, the word immediately after given, is for younger than 30. So essentially we ignore everything else in the table and just look at this column. Then from there, probability of using medication. So within this column, using medication is going to be 200 out of a total of 520 people. This first one was just using conditional probability formula. This is using that little shortcut that we had. There's the 520 down there and the 200 from up here. These ones get a bit more abstract. So this is where using the conditional probability formula is pretty much required. One thing that's worth understanding is anytime you have a conditional probability that's known with other, like sort of, you can almost think of it as like random other probabilities that are thrown at you, the vast majority of the time, a good first step is to expand that conditional probability formula into what it was, the intersection divided by the conditional. From there, we're looking for this intersection, and so all we do is rearrange for that intersection. It's also worth highlighting. The order in which these terms are written in doesn't actually matter. B intersecting A is the same thing as A intersecting B. So by finding this, you do in fact find what we're looking for. So all we're going to do is plug in the terms we already know. Probability of A is 0.5, probability of B given A is 0.8. Smack them together. There's your intersection. Very algebra heavy, these kinds of things. You'll be able to notice them pretty quickly by just the fact that they're super abstract. Just here's this probability, here's this one, here's this one. You're pretty much always working with algebra at that point. That's all of conditional probability. So if there's any questions about that, don't hesitate to interrupt me. Otherwise, we shall continue on. Okay. That leads up to independent events, which pretty much work exactly as you expect them to, as they sound. Independent events just means that one thing has nothing to do with another. They're independent of each other. So the mathematical, there's a couple of mathematical definitions. The one that probably makes most intuitive sense is to say that A given B is just the same thing as A, effectively saying that B had nothing to do with the probability of A. What tends to be a bit more useful, even though these are technically the same statement, is to say that the intersection is the product of each of those terms' probabilities. So A intersecting B is the same as the product of probabilities, A and B. These are fundamentally the same thing, but this tends to be more available immediately. So if you ever want to prove independence, you're looking to prove either this or this, whichever one seems more natural to you. It's up to you. So for that, again, we're going to have one of these tables. We want to prove that male, well, I guess gender and music or movies, whatever their recreational choice is, we're going to prove that they are either independent or not independent based on the results we get. The good news here is that you can actually pick any elements you want. You can pick male movies, you can pick male music, you can pick female music, you can pick female movies. It doesn't actually matter as long as you go diagonally. Don't choose like male to female or music to movies. As long as you pick the events that are actually contrasted together, you'll be fine. So here's one such example. I've got two in the notes. We'll only go through one. In this case, I'm going to test the intersection is equal to the product of those two things. So first things first, find that intersection. Male or movies, well, that's going to be 75 out of a total of 700. Now, I've shown you a few tactics on how you can simplify that down, but otherwise, we've got our target probability. From there, we need the probability of male and the probability of movies. Male is a total of 300 out of 700 people. Movies, we've got 175 out of a total 700, and so that's where these two probabilities are going to come from. All we're going to do is see, does the product of those two things equal our intersection? Sure enough, they do, hence independent. If they don't, so if I go to another example, we had intersection was 1 out of 5, Y was 3 out of 5, less than 30 was that. If you multiply those two things together, you'll see they're not at all the same. Hence, these aren't independent. You can kind of get an idea ahead of time what you would expect the answer to be if you think somewhat logically. Some of them are a bit harder to justify, like this one here about the like gender, music, and movies. You might say there's a slight skew, but kind of hard to say who would be more interested. Whereas with this one, probably a bit more appropriate to assume that people that are older regularly use medication more than people who are younger. So that can sort of inform what you expect your result to be. Although I'm sure there's going to be some circumstances where someone's writing these questions and they just completely forget about what the actual scenario is. So, not saying you won't see weird things, but more often than not, you should be able to get an idea of what you expect the final result to be. So that's not quite all. You can use the property of independence if it is told to you that the events are independent, and that can help you find specific probabilities, namely the union, because the union equation actually has an intersection in it. Normally, you can't just sort of look at a thing and say that's the intersection. Well, maybe that's not quite true, actually. There's a few examples I can think of where you can. Point being, it gives you another way of getting that intersection where you otherwise wouldn't be able to. So, probability of owning a pet is independent of owning a car. So basically, whenever you see that word independent, you should be immediately thinking of the fact that the intersection should be the product, or the conditional should be the same as without the conditional, either of those two approaches. Given a bunch of probabilities, whatever, point is we're looking to find the probability of getting either a pet or a car or both. So that key phrasing there implies union. We want to have pet or car or both, and the union equation is as follows. You want to find the addition of the two individuals and then subtract one copy of the intersection. The fact that the events are independent means that you can replace this intersection with the product of those two individual probabilities. That's good news for us because we actually have both of those. Probability of car, 0.75, probability of pet, 0.25. So we're just going to replace this intersection with that product and then just slide in those numbers and simplify down. Again, if you prefer fractions, by all means, make these 1/4 and 3/4 respectively. That can make things a bit nicer if you like that. Otherwise, this is another way of doing it, decimals. Anything to clarify there? Don't hesitate to interrupt me. Sometimes it gets a bit more complicated, right? So we're going to have independent, sure, and we're going to have union, sure. Now it gets a bit weirder. So these kinds of questions actually sort of dive back into quadratics, where effectively what you have is you're trying to find the minimum or maximum of a certain thing. So as soon as you see that key phrasing, you should also be thinking about the quadratic applications. So whenever you want to find a minimum anything in quadratics, the first thing you want to do is figure out an equation for that thing. You can't minimize or maximize a thing unless you know what that thing is. So we're trying to minimize a union, hence we're going to start with the union equation, or the addition rule, I think it's called otherwise. Now the problem with this is that there's 3 separate terms, and so that's hard to work with. Can't plot that, can't really do a whole lot with that. You can, but you don't want to use super high-tech software. One of the things we are told, though, is that the sum of A and B is 0.4. So that's pretty nice. We're going to replace that term with just 0.4. That's going to get us down to a single probability in there. Although the intersection is not great necessarily to work with, so we are going to use our independent events formula or property to expand that out into the product of A and B. So it might feel like we've taken a step back. We've got 2 probabilities in there now as opposed to just 1, but the intersection just wasn't really great to work with there. So we've got to figure out another way to get this down to either probability of A or probability of B. Once again, we can reuse this equation here. this is an equation that relates A and B together, and so you can simply rearrange that either which way you want. As follows, I've chosen to rearrange for A, you can rearrange for B. It doesn't actually matter. You just want one or the other. So every probability of A in our equation, so just this one here, is going to be replaced with our expression for it. That's what this bit's all here for. This goes to this. From there, you can expand this out, and lo and behold, you have a squared term in there, hence you're working with quadratics. This is a positive quadratic, which means your minimum is going to be at a turning point. Just for fun, here's what this would look like if you were to sketch it. Reminder at the top of the question, this was a CAS question, so you're allowed to sketch these things if you like. So you can use the analyze graph tools if you like. I'm not really much of a fan of that because it doesn't give you an exact value, so better off using the sol function on your CAS. That's going to give you a probability B is equal to a fifth. Now, the CAS syntax, I've put X there because writing PRB in the CAS isn't going to do a whole lot. So just keep in mind when you're doing these things on the CAS, you might want to like write to the side what that substitution is and then replace it with the actual term.
Hey, Chris.
Yo.
What's the d on dx?
Oh, yeah, okay, this is derivatives. Ha, I just realized I've written this in the context of finding... Yeah, okay, that's derivative. So if you haven't done that, I wouldn't worry too much about that just yet. So the alternative of using the derivative approach would be to do completing the square. You could do axis symmetry. Anything like that would also work. Even the fmin function, actually. Any of those would be an alternative if you haven't come across derivatives yet. Yeah, most schools will do probability after calculus, although I guess some do it back to front. So yeah, no, good question.
Okay. Oh.
Didn't realize actually I wrote a note to make sure I'll make it a bit more globally solvable rather than just having to use derivative. Let's say fix, what's this one? Independent derivative. Cool. All right, I'll sort those out by probably tonight. But okay, point being, that's which method you use to find your turning point of a parabola, you're going to get x equals a fifth, or in this case, our x was probability of B is a fifth. So to then find our minimum value of the union, you're just going to replace all these probability B's with a fifth, and that's going to give you the, well, minimum possible probability of that thing. Any further questions about that? Cool. Okay. Last up, mutually exclusive. Do I not have a video for this? No. Another thing to add to the notes. Anyway, mutually exclusive events. So it's kind of a similar vibe to what we're doing with independence. The definition of mutually exclusive simply means that there's no intersection between those events. So the probability of that intersection would therefore have to be 0. So the way these look on... Do I have a Venn diagram here? No, this one's short. If I just open up the phone again, go to the handwritten bit, fundamentally it's just a Venn diagram that doesn't intersect. So you have set 1, you have set 2, and there is a gap between the two. There is no intersection. That looks suggestive, so I'll just get rid of that. And then go back to the printed notes. So, prove events are mutually exclusive. You just want to show that the intersection is 0. So, we're told the conditional probability is 0. Can those events be mutually exclusive? Potentially an interesting question. We kind of come across it before, which is if you're just chucked some random probability that is a conditional probability, a pretty decent idea would be to expand that out into the intersection divided by the conditional. From there, once you have that, you need to look at that and figure out, could this ever be 0? Well, the only circumstances by which you have to look at it and say whether the intersection could potentially be 0. And well, in this case, If the conditional probability is 0, the only way that the probability could be 0 is if the intersection was 0. You can't do much about this denominator. You can't make it negative. That's, well, not possible for the fact that probabilities can't be negative. And you can't make it 0 because then you'd have a divide by 0 issue. You'd get undefined. So really it's all about this intersection here. That's the only way that this statement here could ever be true. For that reason, the events are independent. So I guess that's another way you can have mutual exclusivity. If you can prove the conditional is 0, then that's another way of doing it. Although, if you can prove the conditional is 0, you can also prove the intersection is 0. Though, to be fair, it is also the same sort of situation up here, where if you can prove the intersection is the product, you can also prove the conditional, because the conditional needs all of these. So, I guess that's just a preference thing. Here's one that's a bit more interesting. You've got two probabilities. You know nothing else about them. Can they be mutually exclusive? Bit of a weird question. Well, one thing you have to do in this circumstance is consider the union. So mutual exclusivity simply means you need to prove that the intersection is 0. So we need to think of ways to get an intersection into our equation, whatever that equation happens to be. The union equation is a decent example of that, so we're going to start with that one. Union equation, A plus B minus the intersection is going to give you the union. So we need to now look at this and think, could this intersection ever be 0? Well, let's test it. If you put a 0 there, then the union is going to be given by A and B. Under those circumstances, the number's going to get bigger than 1. So for that reason, the intersection could never be 0, because then the union would be too large, impossible. And so what would that mean? Union, I guess, the intersection rather, would have to be at least 0.2 for that to work out. And then you can use it to solve mutually exclusive probabilities as well. So if you're told your events are mutually exclusive, then you can use the fact that the intersection is 0 for solving it. So again, this is going to be pretty handy for unions. I've just sort of jazzed it up a little bit because otherwise it's basically the same as this question. I've done x and y dash. So I've done that just so you can see how those terms get plugged in. The union of x and y dash would be x plus y dash minus the intersection of those two things. They're both equal to 0.4, so both of these get replaced with 0.4s, and, well, intersection between mutually exclusive events is going to be 0, so we just ignore the intersection altogether. And I didn't highlight that green. Of course I didn't. Green. Mutually exclusive.
Chris, isn't it possible that x and y dash is just the same event?
Probably. Is it
Or
possible?
does it not matter because they didn't specify?
Yeah, I mean, the answer is it doesn't matter, but the other answer is, yeah, they could be the same event. I would say just because they have the same probability doesn't necessarily mean they're the same thing. Yeah. It's possible, yeah. They could be the same, although it'd be a bit weird if two things labelled a little bit differently were the same. Like the inverse of one will be the same as the other. Not impossible though. We had the lines, the production lines A and B. So not B is the same thing as A. So yeah, under those circumstances, could be the same. But otherwise, yeah, that's fundamentally it in a nutshell. That's a really easy summary. Just intersection is 0. That's all you need. Cool. So that basically concludes the lecture on that. We got conditional probability, we got independence, we got mutually exclusive. Typically, most people struggle with conditional probabilities, so that would be my recommendation on what we do questions. But I'm open to hearing if you want to study any of these as well. So I'll pause for a moment if you want to do anything differently. All right, let's crack on. So we'll go top to bottom on these essentially. In this case, question 1, we have a dice that's rolled. Event A is rolling a 6. Event B is rolling a number greater than 2. Find A given B. So I'll throw that to you guys now. How could we potentially find A given B? There's actually a couple of options. I'll drop the PDF in the chat as well, so you can have a browse for those. Oh, whoops! I got the
What
independent.
question was that, Chris?
Question 1, the first one on there. This.
Is it just 1 out of 6?
Not going to be 1 out of 6 for this one. So 1 out of 6 would have been the probability of rolling a 6. That's probability of A. But this conditional here means you've got to further restrict that sample size.
Wait, no, hold on. So if we're looking at rolling a number, so we're trying to look what's the probability of B given A, right?
Other way around. This is A given B. So the thing on the left is the probability you're looking for. The thing on the right
Oh,
is the
okay.
conditional. Yeah,
So it's just 1/4 then,
1
because
over
we've
4.
got 4 numbers.
Yeah.
And
Was that a Venn diagram approach that you used?
not really. I just thought that
Hmm.
after 2, there's only 3, 4, 5, and 6, and then
Yep.
out of that, rolling a 6 is 1/4.
Yeah, okay, cool. So basically, it's basically kind of a Venn diagram, except you're using like your sets, right? So like set A in this case, rolling a 6 has 1 element in it. Set B has numbers greater than 2, which, as you said, was the 3, 4, 5, 6. You've got 4 total elements, one of which is the target thing you're looking for, hence 1 out of 4. Yeah, that's nice and good. There was also the possibility of doing the conditional probability formula, although that would be probably a bit heavyweight, where you find the intersection of the two, so probability A intersect B, and then divide that by the probability of B. But that's probably a bit much for the scenario we have. All right, question 2 is basically the same thing, so I'll leave that one there. Question 3, however, slightly different, but we did look at a... Oh, this one's actually forcing you to use Venn diagram. Yeah, you can practice that if you want. I'm not actually fussed which way you do it. As long as you know how to do it with a Venn diagram, I'm fine whatever way you do it. Question 3.
Chris, is this 7 over 12?
7 is the correct numerator. 12 is not the right denominator. And I'm pretty sure I know why you said 12. 12, yeah, 12 was a number you had, well, maybe I'll just draw it out. You would have had a 12 here, you would have had a 7 in here, and a 12 in here, V for violin, P for piano. Did you look at this and say, there's a 7 here, there's a 12 there, so 7 out of 12? You're muted if you responded.
I try to like put into the formula the probability A intersect B,
Oh, yeah.
probability B,
Okay, that's
but
good.
maybe I got the numbers wrong.
Um, so the thing that you got slightly off was this bit here. This one here is not how you do probability of P. This spot on the Venn diagram is P without V. P is actually the sum of these two things. Does that change things? Sweet. All right, try that again. See how you go. Any luck with that modification? 7 over 19? Yeah, there we go. 7 over 19. So for everyone else, I'll do a run through. Where was it? It was question 3. So 12 play violin only, 12 play piano only. That's where those two 12s on the Venn diagram came from. And then this one here, 7 students play both. So that pretty much fills out the Venn diagram there. From there, it plays violin given piano. So we're looking for the probability of, let me double check again. Yeah, probability of a violin given piano. Jeez, I can't talk today. Violin given piano. There we go. So a couple ways you could do this. One is to think about like the restriction, where you look at your Venn diagram and say, okay, P is the restriction, so I'm going to ignore everything else and just focus on this bit in the middle. 12 and 7 are going to make 19 for total number of elements, 7 of which are violin. Hence, you're going to have your 7 over 19. Otherwise, you could do the conditional probability formula, which is the intersection of V and P divided by probability of P. Intersection, you've got 7 out of a total of, how many people is this total then? 24, 31? 24, no, that doesn't make sense. Oh, it was 31. So 7 out of a total, 31. That's going to be your intersection. And then for the probability of P, you got 12 plus 7 out of a total of the 31. Hence, from there, you're going to have the 19 out of 31. All I've got to do is divide these two things together. which means flipping that over. 7 out of 31 times 31 over 19 cancels 7 out of 19. So either which way will get you there. Anything to clarify further? Feel free to let me know. Otherwise, we move on. So, yeah, question 4 is unique enough. We'll do that one. And in the meantime, I'm going to take these jumpers off, otherwise I'll cook. I'll be 1 second. One out of 36. Seems I arrived just in time. I see why you did 1 out of 36 there. It's not quite there though. So you wouldn't do the product of those two events. 1 out of 6 by 1 out of 6 would give you 1 out of 36, yeah. As for, well, I guess I'll ask what method were you using for that? Did you try Venn diagrams? Was it the conditional formula?
Wait, Chris, I just reread it and I was gonna ask, is it just 1/6 because the dice always show the same number?
Yeah, yeah, correct. Given the dice show the same number, that means your sample size is just 1, 1, 2, 2, 3, 3. So you still got 6 elements, one of which is double 6. Yeah, so this one here was like, yes, I guess you maybe misinterpreted that the first time as just what's a double 6, which, yeah, that would be 1 out of 36. But yeah, this one here, you can even do like the sample space thing we looked at above. Yeah, if you look at the handwritten bit again, the sets A and B, you could just look at those and yeah, grab your probability nice and quick. Cool. Question 5 is kind of a repeat of question 3, so I'll leave that there. Question 6, however, is using that table of values now, which is still technically a repeat of questions, but it's just presented differently. Table of values and Venn diagrams are basically the same thing. So, question 6.
Are we on question 6, Chris?
We are on question 6. Yeah. Maybe I should put those in the chat every time I submit one. Q6. There we go. I'll see if I remember to do that from here on.
Chris, when it says given that the person is male, does that mean like we just assume that who we're choosing, like the sample space we're choosing out is going to be male, or like
Mhm.
do we need to like factor in the possibility that the person being chosen is a male?
So yeah, where's the actual phrasing for it? Given male. So the thing immediately after the word given in, like, I can't even imagine a context where this would be incorrect, but pretty much every single time I've seen it, the word or the thing after the word given is your restriction. So given male means you only care about that column of male. Everything else you just block out. Ignore the female column, ignore the total column. Your new total is 60, yes is 35, no is 25.
In that case, is the probability just 7/12?
7 over 12 is correct. Yeah, 7 over 12, the simplification of 35 over 60. You got yes and total of 60. 35 divided by 60. Yeah, simplifies down. Cool. All right. If anyone wants me to clarify that, let me know. Otherwise, this one here is just another version of that. More things, but it just means you're blocking out more of it. Here we go. Some of these like random probability mix mashes. Let's give question 8 a shot. Put that in the chat. Q8.
Is the answer to both of them 0.1?
0.1 to both questions?
Yeah, to the intersection and the conditional probability for question 8.
Not quite. So 0.1 being from here? Is that where you got that from?
Yeah,
So what's your logic for why these are both 0.1 then?
because since there's like only two events, right?
Yep.
Then I thought that like the probability of B given A
Mhm.
would that's just like the intersection, I thought, but maybe I'm wrong.
Nah, so the intersection and the conditional are different. If I go back to the screen share bit here, here's a pretty visual example, which is you got two events, roll greater than 3 and even. The intersection of those two events is the middle bit there. That's your intersection. Whereas conditional probability means this divided by this. So slightly different things that are going on. Conditional has intersection in it, but that's not the end all be all of that story. So you've got a couple of, well, I think there's actually only really one way of going about this, which is whenever you're given a whole bunch of terms like this, one of which being a conditional probability, you expand that out to your conditional probability formula. So this would instead be written as B intersection A divided by A is 0.1. So I'll write that on the handwritten bit. We started with probability of B given A,
Would it be 0.06?
0.06. Let me, for part A, question 8. Yeah, 0.06 is correct. Nice. Are you going to do what, or did you do what I did here, which is to rearrange this probability formula?
I did what's it called? It was PR times PRB given A.
Yeah, yeah. So fundamentally, you're just rearranging. Did you rearrange that yourself, or do you just have that formula from somewhere else?
I have it written down.
Yeah, okay, that's cool. So where that came from for everyone else is just a rearranged version of the conditional probability formula. So PRB intersect A divided by PRA. If you know none of these terms, you can rearrange to get either of these on their own, right? So you can multiply both sides by PRA. That's going to get you the intersection on its own. And, well, that's effectively what was done. So this conditional is 0.1. The probability of A is 0.6. If you go 0.6 over to the side, that's the same thing as multiply both sides by 0.6, which is why that intersection is 0.06. Nice work. That follows on quite nicely to part B. The answer there will feed on to that. So we'll have a go at part B as well.
Chris, for question B, would
Yep.
it be PR of A given A intersection B over PRB?
Yes, it would. Yeah.
Okay. Would it just be 0.2?
0.2 is correct. Yeah, precisely. 0.06 divided by the 0.3 is going to give you 0.2. If you don't like decimals, then feel free to make that as 3 over 50 divided by 3 over 10. You could flip that around and then make that a fraction if you need to. Anyone else? But yeah, that one's a pretty stock standard. Like once you have A intersect B, it's a pretty stock standard. Just sub into your conditional probability formula. Cool. Alright, that's that one. Let's see, is there anything else like tough in here at all? That's a duplicate, duplicate, kind of a duplicate. Question 10 is slightly different because you're using a different, like we haven't used unions before, or at least we haven't used them in this exercise yet. So we'll go question 10. Put that in chat. Geez, the wind's picking up around here. I don't know how loud that is over the mic, but it's definitely loud for me.
Would question A be 0.5 plus 0.4 minus 0.7?
0.5 plus 0.4 minus. Yeah, precisely.
Yeah.
So yeah, that'll just be a rearranged version of the addition rule, right? The union is the addition of A, B, and subtracting the intersection. So all he's done there is rearrange that. That'll be A. That'll set you up nicely for B and C, actually. In the meantime, I'll just write out part 10A in case anyone was lost there.
Chris, is 10b just 1/2?
B is, yeah, 1/2. Yep, a half, precisely. Yeah, that one there is kind of a repeat of the previous, which is just plug into conditional probability formula. You have the intersection, you have probability of B, so you just divide those two things. Yeah. And C is 2/5. Yes, 10C is 2/5. That's correct. So once again, very similar scenario, but you have to be aware of the fact that B intersecting A is the same thing as A intersecting B. That's why solving that is still pretty doable. You just got to divide by the PRA rather than the PRB. Yeah, that's about it really. So I guess for the remainder of this, I'll just sort of talk about these feel like extended responsey kind of things. Let's see. So current football fixture, playing at home for 60%, plays at home, team wins 80% of the time. There you go. So that's a sequence right there. They play at home 60% of the time, and when they play at home, they win 80% of the time. So just to start what that would look like, a pretty good way of doing this would be a Venn diagram. So you'd have either home or away. So I'll say H or A. And then, well, the one that I know, home and win, home and loss. Home and win is going to be 80%. Yeah, when it plays at home, team wins 80% of the time. So 0.8 going there. Home is 0.6 for probability. And then you just fill out the rest from there. So if that's 0.8, then this one has to be 0.2. If home is 0.6, then this one has to be 0.4. And then from here, I haven't read the rest of the question yet, but I'm sure there's going to be at least one of these given to us. Yeah, there you go. When it plays away, the team wins 40% of the time. So you do your 0.4 there, your 0.6 here, and then you just answer whatever question, which is what percentage of the games does the team play away and win? Away and win means you go here, then here, hence 0.4 times 0.4. So a lot of these probably better off done with a tree diagram. There's a whole bunch of them there. Wow, there's a real whole bunch of them there, hey. You're even going to have one of those max or min style questions, or question 21. Those are always going to be tech active, so they're still tough, but not as tough as if you had to do it by hand. But alright, that's pretty much it for that. So if you have anything you'd like me to quickly clarify, I'll stay back for like a minute or two. Otherwise, enjoy the rest of your day.